Hello, calculus students. Today we are going to move forward in our discussion of differentiation. And in this particular lesson, we are going to look at something called implicit differentiation. The objective for today's lesson is for you to be able to distinguish between a function that is written in implicit form versus one that would be written in explicit form, and to use implicit differentiation to find derivatives of a function, or even of just a curve that maybe isn't a function. Most functions we've expressed so far in this class have been written explicitly. So for example, y equals 3x squared minus 5. This is written in explicit form. All that means is that we've got y by itself and then all of the x terms on the right side of the equal sign. Some functions, however, can only be implied by an equation. For instance, consider the function y equals 1 over x. It is defined implicitly by the following equation: xy equals 1. Suppose you were asked to find dy dx for this equation, find the derivative. You could begin by taking the implicitly written form of this equation and write it explicitly. In other words, solve it for y, and then everything on the right-hand side would be in terms of x. Then just do your derivative with respect to x, and you'll get your result, which is negative 1 over x squared. This strategy works whenever you can solve the function explicitly. You cannot, however, use this procedure when you are unable to solve for y as a function of x. Consider the following equation: x squared minus 2y to the third plus 4y equals 2. How would you find dy dx of this equation? It's actually very difficult. In fact, I would encourage you to try to write this in terms of y equals and then all the x stuff over here on the right. So how are we going to find the derivative of a function like this? Can we do it? The answer is yes. We can use implicit differentiation. To understand how to find dy dx implicitly, you must realize that the differentiation is taking place with respect to x. This means that when you differentiate terms involving x alone, you would just differentiate them just like you normally would. However, when you differentiate any terms involving y, you must apply the chain rule. So this is why I waited to teach this lesson until after we've done the chain rule, which is what we did last week. Because you are assuming that y is defined implicitly as a differentiable function of x. So for example, let's look at some different problems where we're going to differentiate with respect to x. So of course, if I ask you to find d dx of x to the third, we already know we can use the power rule. Everything agrees, so we're simply going to use our power rule. That's it. No big surprise there. The derivative of x to the third is 3x squared. However, if we look at example B here, it says d dx of y to the third. This is nearly the same equation as the one above, but now we've got a variable of y. We're still doing our derivative with respect to x, so here we have to use the chain rule. The variables don't agree. We're taking a derivative with respect to x, but the variable is in terms of y. So do the derivative like you would if it had been x, and so the y cubed would become 3y squared, but then you also have to write this u prime term, the derivative of y with respect to x. Here's another example. Here we have two-term binomial. One has a term in x, one has a term in y. We notice that in this case, we can do the derivative of x, no problem, that's just one. But when we do the derivative of 3y, the derivative of 3y is going to be 3, but then we add on this extra term, dy dx, or extra factor. Let's say that dy dx is the extra factor. I also should note that when you're doing these implicit differentiation problems, another equivalent way you could write this answer is you could write 1 plus 3y prime. And that's acceptable if you prefer to do that. When you see me doing examples in class, a lot of the times you'll see me write dy dx, but y prime, just like that's written here, is fine. Final simple example here I want to show you. This one's probably the one, if I was going to ask you to star one, it would be this one. And that is, what do we do when we have, look at this, we've got x times y squared and we want to find the derivative. Well, we have to do the product rule, which if you recall our mnemonic device, it's 1d2 plus 2d1. So we're going to leave 1 alone. That's x is 1, so 1 is alone. Then we got to do the derivative of the second part, plus leave the second part alone, do the derivative of the first part. So when we do this first derivative here, we notice that the derivative does not agree with the variable, so we have to do the chain rule. So the derivative with respect to x of y squared would be 2y dy dx. But then when we get over here, the variables do agree, so we just do our derivative like we normally would. So now we just get rid of the parentheses and we get 2xy dy dx plus y squared, and that's the answer. Here are some rules for implicit differentiation. Number one, differentiate. This is when we have an equation, which is what we've done so far pretty much. Differentiate both sides of an equation with respect to x. Collect all terms involving dy dx to the left-hand side of the equation. Move all the other terms to the right side. Factor out the dy dx on the left side of the equation, and then solve for dy dx. And I'm going to do 2 examples of that, and then that'll wrap up the day. I'm not going to do any examples with any transcendental functions like e to the x, natural log of x, or things like this. I'm keeping all of the examples today based on polynomials because I want to focus on what implicit differentiation is and not get too hung up on, you know, doing the derivative of a sine xy or something like that. But all these rules apply to those transcendental functions and trigonometric functions as well. So here we have a function, or I'm sorry, here we have an equation. This actually isn't even a function. It says find dy dx given that y cubed plus y squared minus 5y is equal, or minus x squared is equal to -4. Now, it shouldn't be too hard for you to realize that there's no way you're going to be able to solve this for y. You're not going to be able to write this explicitly. So to find the derivative, we're going to have to do implicit differentiation. So we're going to do step 1 in our table, which is to differentiate both sides with respect to x. So all I've done here is I've written everything on the left-hand side, and I'm going to do the derivative with respect to x. Everything on the right-hand side, do the derivative with respect to x. Next step, now I'm just going to apply one of the derivative rules, which says that I can break each of these terms separately and do those derivatives with respect to x. And now actually perform the differentiation. Notice that on these first 3 terms on this side, the variables don't agree, so we have to do the chain rule. So the derivative of y cubed right here is going to be 3y squared, and then you have to add this extra factor of dy dx. However, when we did the derivative of x squared, since the variables agreed, it's just -2x. And don't forget the derivative of a constant is just 0. So we've only done step 1, which is to do the derivative with respect to x on both sides of the equation. Step 2, collect all the dy dx terms on the left side of the equation and move everything else to the right. So the only thing on the left is the dy dx terms, and on the right we've got everything else, which in this case is just 2x. Now we're going to factor out the dy dx. So notice that each term on the left-hand side has a dy dx, so we can factor that out using the distributive property. And now finally, we can solve for dy dx. So the only thing left over here with the dy dx is this here. So we're just going to divide it over to the other side. This gives us our final answer. dy dx of our original equation is 2x divided by 3y squared plus 2y minus 5. Now you might think, wow, that's great, but why is that useful? So let's see how that would be useful. So the curve that we just did the derivative of is shown here in this graph. That is the equation y cubed plus y squared minus 5y minus x squared equals, I think it was -4. Yeah, sorry, kind of got cut off there. That's the graph. So what if I asked you, what is the slope of the tangent line at the point 2, 0, at this point right here at 2, 0? Well, the way you would do that is you would just simply plug x equals 2 and y equals 0 into this equation. Of course, on the numerator, you're going to get 2 times 2, which is 4. And then the denominator, since y is 0, you're going to get negative 5. So that tells us that the slope of the tangent line right there is negative 4/5. In fact, we can actually find the slope of the tangent line anywhere on this curve with this implicitly found derivative. It's very, very powerful and useful. And we're going to see that next week when we start looking at related rate problems. Okay, this is my third and final example, and we'll call it a day. So this one says determine the slope of the graph of 3 quantity x squared plus y squared equals 100xy. And we're trying to find the slope of this graph at 3, 1. So the first thing we're going to do is we're going to do the derivative with respect to x on both sides of the equation. Now notice that this, first of all, let's focus on the right-hand side of the equation. Here we have a product, so we have to do the product rule here. Now remember, that 100 is a constant, so I just pulled that out to the front, and now we got to do the product rule of x, y, this derivative with respect to x. So we've got to do, remember, this is 1, and this is 2, so we're going to do 1d2 plus 2d1. The right-hand side, we have to use the chain rule on top of the chain rule. Again, I pulled out that factor of 3, and then I did the chain rule. So this 2 comes to the front. That reduces this exponent to a power of 1. I left the inside of the parentheses alone, and then I have to do the derivative of the inside. Well, the derivative of x squared is 2x, because that's just the x and the dx would agree. But then when I do the derivative of the y squared, I have to do my chain rule. So that's going to be 2y dy dx. Let me erase what I have here on the slide. Now what I want to do is I want to just clean this up a little bit and get all of the terms with dy dx on the left-hand side. So notice I have everything over here is only in terms of dy dx factors. Everything on the right, there are no dy dx's. So we're still there. I'm going to factor out that dy dx. So notice I had a dy dx factor here and a dy dx factor there. I factored that out. That's step 3. And then last but not least, we're just going to divide this whole expression to the left. You'll notice that they all have a common factor of 4, and we can clean things up a little bit. And we get the following dy dx. This is the derivative implicitly for that particular equation. As you can see, this one's a little bit more complicated. So how is this useful? Well, this is the curve. This is the graph of that curve. It's something called a lemniscate, and it's a figure 8. This one's actually tilted a little bit to the right. And if I wanted to find the slope of the curve at the 0.31, the 0.31 would be right there. I would just plug 3,1 into the derivative that we found in the previous slide. And so I plug in those numbers. That gives me 25 minus 90 over negative 75 plus 30, which becomes negative 65 over negative 45, which gives us an answer of 13/9. The slope is equal to 13/9 at the 0.31. Pretty crazy, huh? Pretty crazy, I think. Notice this function is not, this isn't even a function. It is a curve. It doesn't pass a vertical line test, but we still can use our calculus to figure out slopes of tangent lines. Again, next week when we meet with the next week's lesson, we're going to look at something called related rates, which is where we're actually going to start applying the concepts we've learned in this chapter so far to real life problems. Let's go ahead and end our presentation there. Thanks for your attention.